Okay, so we're back. Um, sorry, this is from fall of 2014. It is exam number 2, Engineering Science 2143. Okay, so we're just going to go through it again. At home, you should be working these by yourself to see if you can even get them set up, and then look at the solutions and come watch the videos, okay? So we have a load is being applied to a 10 by 10 by 20 10 by 10 by 20 cube of material. The load is applied through frictionless plates. Materials tested were performed, and the stress strain diagrams were developed for both normal and shear stress and strains. Okay, so I'm going to note that this is axial, and then we had a shear test so we could determine the shear strain. When I look at this, I know that this is going to be my yield, and this is my ultimate, and this is my yield. The slope of this line is my shear modulus. The slope of this line is my MOE, my Hooke's law. It's the modulus of elasticity. So what is the load P that results in yielding? Well, I have to know load P, we're pushing down. This is not a shear, so we're going to be looking at our axial, and yielding occurs at 75 KSI. So I know that my yield stress is 75 KSI, and that stress equals P over cross-sectional area. So that's that force P. That's the axial force that I'm looking at. And my cross-sectional area is, okay, it's whatever it's pushing down. It's that perpendicular to that surface. So that's 10 by 10, which is 100 inches squared. So my P, that force P that causes yielding, is 7,500 kip. Okay. The ultimate load P that can be carried. Okay, well, that's going to be this value up here. I don't know why I have a Y there. That should be a U. Okay, I know that that is going to be my ultimate stress, and stress is just internal normal over area. So let's look at that. My ultimate is 100 KSI. That equals the force P divided by my cross-sectional area. So I get that P equals 10,000 kips to cause that ultimate stress. What is the vertical displacement at 5,000 kips? Well, I know that my yield is at 7,500 kips. So this tells me that when I'm at force of P at 5,000, I'm going to be in that elastic region. So this is an elastic load. And as such, I can use this relationship right here because it's going to be less than the yield, and I could find E. Or I could also, okay, it's just going to be a relationship of 75 is to 0.003 as whatever this stress is, and find the strain that way. But vertical displacement, that is delta. Stress equals E times strain. Normal force over area equals E times delta over original length. So I've got to find E. E is my slope. It is rise over run, 75 KSI divided by 0.003 inch per inch. So I get an E value. I get an E value of 25,000 KSI. Okay, so now let's look at this. So the stress that we're looking at, it's 5,000 kips. 5,000 kips divided by 100 inches squared equals 25,000 KSI times delta divided by original length, 20 inches. When I calculate this out, I get that my delta, my change in length, is 0.04 inches, and it's going down because actually that's a negative because we're in compression. So I should get a delta that's negative, okay? But I kept that in the back of my brain so I can tell you instead of a negative 0.04 that it is a 0.04 going down. And yeah, you need to let us know, is it going up or going down? Okay, it's going down. the vertical displacement at P equals 9,000. Well, now I have to go back and I can, oh gosh, 9,000 is bigger than 7,500, but less than the 10,000 right here. So here is my 9,000 kips. I mean, my 9,000 kips. So I'm going to calculate what is that stress. Stress is 9,000 divided by area, and I get 90 KSI. So I'm going to put that up here, 90 KSI. I'm going to draw over, and then I can come down. Well, the nice thing is I have this nice smooth line, and so I can use the slope of this line to actually calculate the actual value of strain and not my made up, I'm going to guess. Okay, so let's look at, okay, 100 minus 75. 100 minus 75 is 2, okay, 0.0125 minus 0.01 as 100 minus 90 is 0.0125 minus the strain at 90. Okay, and when I do that, then I can actually calculate, okay, I can calculate that strain, and I get that the strain at 90 is 0.0115. Again, this is a negative strain because I'm compressing, but I'm just going to keep that in my mind. And what is strain? Strain is change in length over original length. It is change in length over 20 inches. So if I multiply this strain of inch per inch times 20, then I'm going to get a delta of negative, okay, 0.23 inches, which is a delta of 0.23 inches down, or short, whatever you want to, I'm going to call it shorter. I know that it's going in the shorter direction. Okay, the cross-sectional dimensions at 5,000 kips. Okay, well, 5,000 kips, again, is back in this elastic region. So I can use Poisson's ratio, okay, because I know that that is the lateral strain and the longitudinal strain. And I can find the longitudinal strain because actually I already found the delta, so I can just divide that by the original length of 20 inches to get my strain. So I need Poisson's ratio. Well, how do I find Poisson's ratio? That was not given, but I can go back to my equation sheet, and there we have the relationship. Okay, there we have the relationship. So I need my shear modulus. And again, it is just the slope of my shear stress strain diagram. So I have 30 KSI divided by 0.00324 radians. And I get that the shear modulus is 9,259.26 KSI. And if I know my shear modulus and I know my modulus of elasticity, G equals E divided by 2 times 1 plus Poisson's ratio, okay? I can plug in the 9259 here and the 25,000 here, and lo and behold, I can get a Poisson's ratio of 0.35. Okay, so now I can come back. I have Poisson's ratio. My longitudinal strain, what does that come from? It came from, okay, P equals 5,000. I already found my delta of 0.04, and I know that strain is change in length over original, so I have 0.04 divided by 20 inches. And if I cross multiply and divide, okay, cross multiply and divide, but wait, I need to think. Is this strain, it was getting smaller, so it's actually a negative 0.04. And that's very, very important because otherwise I'm going to be left with a negative here, which means that our lateral is getting smaller, but actually it needs to be positive because we have this strain is negative. It is in compression. It comes from a negative stress. So when I multiply this out, I have 0.35 times negative 0.04 divided by 20 okay, because it's that negative strain. And then we're going to multiply through by -1. So all of this is negative, and that's going to be my lateral strain. So that lateral strain is actually a positive value, and we get 0.007 inches per inch. So now if I want to know the change of the side, and it makes sense it's positive, my cross section is getting bigger, then I'm going to have length, what does it say? The cross-sectional dimensions. So I'm going to have length final minus length initial divided by length initial. I now have 10 times this, which is a positive value, plus 10. So my final length is getting bigger as it should, and I have 10.007 inches by 10.007 inches. And there is my new cross-sectional dimensions.